Hello, this is Richard Liu, and I will be talking about the PUC Value Checker. So, the PUC Value Checker is a continuation from a project done by Grace Larson, Kevin Hua, and Kian Wee. So, to begin, I would like to recommend checking out the previous two PUC videos. You can find them in the EE431 forum page under Kevin Hua and Grace Larson. It would discuss more about the background of this project and its implementation in the DC house. Grace discusses the initial PUC secret tree. Then Kevin would go over the DAC. And while checking them out, I would recommend giving them a thumbs up. So what is the PUC Value Checker? PUC Value Checker essentially is a device to validate an input key against the security code in the KKGR system. So to begin with the high-level diagram, we have input, which is a voltage value between 0 to VDD, and we have a code inside the value checker that it will compare with. If you have a wrong value as an input, the value checker will compute and would produce a 0 on the output. And the case where you have the right value, which will match the exact code or fall within the threshold around the code, it would produce a 1. So what is inside the value checker? Let's just take a look and break down this top level block diagram. Looking inside the value checker, we see two op amps configured as comparators fed into a NOR gate. To explain the operation, we'll start with an example where the code is 1 volt and our finite voltage sources are 0.1 volts. So we see in the top comparator the negative input is 1.1, and in the bottom comparator the positive input is 0.9 volts. Given an input, say 2 volts, the top comparator will see that the plus terminal is greater than negative terminal and gives a 1. The bottom comparator will see that the 2 volt is greater than the 0.9 in the positive terminal, so it'll give a 0. 1 and a 0 through a NOR gate will produce a 0. This is the case when we give in a incorrect key and the value checker will produce a 0. In the case that we are given the correct value, where the input is 1 volt, the top comparator will produce a 0 and the bottom comparator will produce a 0. 2 zeros fed into a NOR gate will produce a 1. And that is correct for validating our value checker. To see how these comparators and the NOR gate are implemented in the discrete level, please give me a minute to grab a refresher. Alright, so let's get back into the PUC value checker and let's go into cadence to implement this in a discrete level. So this brings you back to 308, where the comparator is implemented by a differential pair of transistors. Above it is 2 PMOSs acting as current mirrors, and below it is 2 NMOSs acting as a current source. Then we have two inverters on the output to bring the comparator and into a rail-to-rail output. And in the simulation, we can see that the positive input is this red sinusoid, and the negative input is this green DC at 0.6 volts, and the resulting waveform is the output labeled in pink. It is a resemblance of a rail-to-rail, pretty close to rail-to-rail, from 0 to 1.18, and that is desired for the comparator for the circuit. Next, for implementing the NOR gate, we have CMOS transistors where two PMOSs are in series, and we have complementary pair NMOSs configured as parallel. And the NOR gate would only output a 1 when your PMOS transistors are on. So that's the event where A equals 0 and B equals 0. Then to sum up the comparator and the NOR gates together to the value checker diagram shown earlier, we have a symbolic view with the comparator as a block and NOR as a block, and connect them as shown. And currently I'm working on the layout, and this is what I have so far. It's a work in progress. I'm doing the automatic placement and routing and see how that goes. And that's it for my PUC Value Checker. Hope you enjoy the video and have a happy holidays.